This is the uphill roller. The uphill roller consists of two inclined rails, a cylinder, and a double cone. Now do this. Put the cone aside and get hold of the cylinder. Try to roll the cylinder from the narrow portion of the rails towards the wider portion. What happens? Can you move the cylinder to the end of the wide side of the rail without helping it along? No, I don't think so. Gravity is pulling the cylinder down towards the narrower side, which is obvious, right? Now put the cylinder aside. This time, we'll use the double cone. What do you think will happen this time? Will the double cone A. roll naturally to the narrow side of the rails like the cylinder, or B. roll to the wider side of the rail and go against gravity? That's impossible. No object can go against gravity without help. Well, let's see. Wow! How does the double cone do that? Let's look closer at the rails, and are wider as they go to the higher end. But they also get narrower as they go to the lower end. The rails slope down gently from one end to the other. And so that's why the cylinder, with its constant cross-section, gets pulled by gravity toward the narrow end. But how about the double cone? When you place the double cone at the bottom of the rail and let go, it will roll up the inclined rails as if to defy gravity. All objects behave as though their mass is concentrated at a point called their center of gravity. A simple shaped object like this double cone has its center of gravity at its center, or the middle of its axle. Let's view the demonstration from different angles. When viewed from the side, we can see that the cone comes in contact with the rails first near its center, where it is at its widest diameter. The double cone then rolls up the rails, but as it moves up, the rails come in contact with the double cone farther and farther away from its center until the end of its axle, where it is at its narrowest. This is because the rails at the lower end are closer together than they are at the upper end, corresponding to the triangular shape of the cone. Now let's view the exhibit from the front. If we trace the movement of the double cone along its center of gravity, we can see that its center of gravity is actually going down as the object rolls up the rails. The conic shape of the double cone, the slope of the rails, and the widening of the rails create a setup whereby the center of gravity of the double cone is actually higher at the lower end of the rail than at its higher end. Therefore, even though the double cone does ascend the slope, its center of gravity will actually move downward. It's not defying gravity at all. The concept of center of gravity can be used for a lot of practical applications. Furniture can be designed so that there is more mass at the base of an item than at the top part, so they don't easily topple. For appliances like electric fans, these usually have wider and heavier bases so they stay stable as you move them around.